Hello. I'll go over the one lemma 13.03, and we are given a Fibonacci sequence defined for integers, and m is some fixed positive integer. And we want to show there exists infinitely many integers n such that m divides f of n. And secondly, we want to show that f of n is a periodic sequence modulo m. So for this proof, we're going to first define some terms. So first, Rn will be the remainder of f of n when divided by m. Okay, and we'll also define a set S, where it collects R of n comma Rn plus 1, where n is a natural number. Well, we can actually say this is a real, but it doesn't really matter. I mean, we can replace this for like integers, but it doesn't really matter. Okay, so now what we have to note is that the set S, the size of the set S is less than or equal to m squared. Well, this is because in modulo m, there can only be m different remainders. Hence, we'll have so the two combination of those remainders, it will be maximum m squared. So the size of the set m is m squared. But we notice that n is natural number, right? And natural numbers is an infinite set. Hence, there will be but this is restricting this infinite set. Hence, there will exist by the Pigeonhole principle. By Pigeonhole principle, we can say that there exists and I don't want to use n again. J and k in natural numbers, such that rj comma rj plus 1 is equal to rj plus k comma rj plus k plus 1. Well, what is this equivalent to? This is equivalent to saying that rj is congruent to rj plus k modulo m, and rj plus 1 is congruent to rj plus k plus 1 modulo m. Well, this is also equivalent to saying that, let me scooch this a little bit. This is also equivalent to saying that fj is congruent to fj plus k modulo m, and fj plus 1 is congruent to fj plus k plus 1 modulo m. Well, now this is great because we could go down a sequence. Well, what do I mean by that? Well, because we get that well, let me just copy this over here so I could have more space to write. So this allows us to say that fj plus 1 minus fj is congruent to fj plus k plus 1 minus fj plus k. But what do we know? This is actually fj minus 1, and this is actually fj plus k minus 1. So we kind of can go down and up every time. So now combining this and this, we can get that fj minus 2 is congruent to fj plus k minus 2 modulo m, and we can continue, we can keep on going down like this until we get that f1 is congruent to f1 plus k modulo m. And we can also say we can go down to f0 is equal to fk modulo m. Well, from here we notice that we can prove that they are periodic because f1 is congruent to f1 plus k and is congruent to f2 plus k, 1 plus 2k, and so on. And this also holds for f2, 2 plus 2k, all the way to k minus, it also holds for fk. Well, so fk would be equal to f 2k, which is equal to f3k, and so ever. So we can see that fn is now periodic. Now, how do we prove that there will exist infinitely many integers n such that m divides f of n? Well, we first have to look at these terms. So if we look at f1 plus k and f of 2 plus k over here, we can set up, since f of 1, which is 1, is congruent to f of 1 plus k modulo m, and 1 is congruent to f of 2, which is congruent to f of 2 plus k modulo m, we get that if we kind of subtract these two, so this is kind of informal, but I'll just do it this way. If we kind of subtract these two, we get that f of k is congruent to 0 mod m. And we can also repeat this process actually with saying that 1 is congruent to f of 2, which is congruent to f of 2 plus 2k modulo m, and 1 is congruent to f of 1, which is congruent to f of 1 plus 2k modulo m, and then this will imply that f of 2k is congruent to 0 modulo m. So basically we can basically say that like f of tk will equal to 0 modulo m, where t is some positive integer. Hence there exists infinitely many positive integers such that m divides f of n. Well, now we can kind of expand this idea to integers by defining terms such as f of 0 or like f of minus 1. So we can actually extend Fibonacci numbers to negative numbers as well. Well, in that case, f of 0 will just equal 0. So this can be another way to find the initial one like this. Thank you for listening, and I hope this lemma was very helpful.